So, hi guys. So, we'll start in like 2-3 minutes or so. Like we'll start at 6:05 so that some more people can join the meeting by then. So till that time, can you guys let me know in chat if my if I whether I'm audible? Is my audio clear or not? Maybe you can give a thumbs up or type in chat if my audio is clear to you guys. Okay, great. So my audio is clear. So yeah, so as I said, we'll start in uh, we'll start at 6:05 or something like in 2-3 minutes. So a few more can join the meeting. Okay, so I guess we can start the session since I don't see more people joining till now. So, hello everyone. Welcome to this is the problem solving session 6 of Discrete Maths NPTEL course. So, in today's I'm Lakshya Saggi and I'm the Discrete Maths TA for the Tuesday sessions. So, in today's session, we'll be mostly talking about graphs and like definition more definition related to graphs like subgraphs and problems related to degree sequences and stuff like that. So which you have covered in this week's NPTEL lectures. So I guess we'll just start with the problems right away. So just let me share my screen, guys. So I hope my screen is visible to everyone. Uh, you can let me know in chat if it is not visible, or if it is visible, you can just put a thumbs up. So is my screen visible, guys? Can you guys let me know? Okay, nice. So it's visible. Thanks, Kushi. So we'll start with the problem for today's session. So 1 second. So coming to the first problem for today's session. So We have already, you guys have already seen what are degree sequences in a graph, right? So just first question is basic revision of that. So it's just asking what is the degree sequence of the given graph. So basically we have been given a graph and uh, 1 second, guys, my mouse is not working properly. Let me just change it. Yeah. So So in the first question, basically, we have been given this ordering of vertices. So a degree sequence is generally given with respect to an ordering of vertices. So here the ordering has been defined as this: one vertex has been said as A, the other B, C, D, E, F, and G. So we'll assume that we'll have to give the degree sequence in this order only, in the order going from like A to G. So note that like what I mean to say is here is that a degree sequence where like this vertex is labeled A and this is labeled B, this graph will have a different degree sequence than a graph where like the B vertex is labeled instead as A and A is labeled as B. That graph will have a different that graph can have a different degree sequence. Basically, all these degree sequences will be permutations of each other with respect to the ordering which we have defined. So for now in this graph, we have defined this fixed ordering of this A, B, C, D, E, F, G. So we can just start with trying to list out the degree sequence. So uh, for listing out degree sequence, we just need to list out the degrees of all the vertices. So we can just directly see that degree of A is 4 since there are like 4 vertices going from A. So answer should look something like uh, maybe I'll just type it out. So uh, we need to do the degrees of vertices with respect to the order order of vertices, or maybe ordering of vertices defined by the labeling. That is, list out the degrees of vertices from A to. I hope this statement is clear. It's too difficult to see, so we'll just be writing out the degrees from A to G. So we can see for writing degree of A would be something like it has 4 outgoing edges, so degree of A will be 4. So it will look like first we'll have 4, then we'll have to find a degree of B, which is again 4 since B has 4 outgoing edges, again 4. Then C has three edges. Here we can see C has 3 edges. So then will come a 3. Then we'll write a degree of D, which is again 3 since there are 3 edges going out of D. So, and then out of E again there are 3 edges. So again the 3. And then from F there are 5 edges, actually 1, 2, 3, 4, 5. So, 5. And then in the end G has only 2 degrees. So the answer will be something. The answer should look something like this. So 4, 4, 3, 3, 3, 5, 2. So the answer is for this question will be like the C option, since C option is exactly this, like 4, 4, 3, 3, 3, 5. So answer is a straightforward question based on basic definition of degree sequences. Nothing too difficult, but I guess still we should be trying out these sort of questions. So we actually know how to write out the degree sequence of a graph. So, so let's come to the second question then. So the second question. 1 second, guys. So the second question is asking us that what are the cut edges and the cut vertex respectively in the following graph. So we have been given this graph which has like labeling of nodes. So we need to find out what are the cut edges of this graph and what are the cut vertices of this graph. So There can be, as you have already seen in the lecture, there can be multiple cut edges as well as multiple cut vertices for a graph. So we'll just try to list out, and the definition of cut vertex and cut edges is uh, we have already seen in the lectures that a cut edge is an edge whose removal or deletion and disconnects a component. So cut edge for this graph will be an edge whose removal with this whole graph is a one single connected component. So a cut edge would be an edge whose deletion will create instead two components which will disconnect the graph. And similarly, the definition of cut vertex is a vertex whose removal disconnects the component. So an edge or a vertex. So when we are deleting a vertex, we'll delete all the edges around that vertex also. So just going by these definitions, let's try to find out the cut vertices. So we'll just go over all the vertices one by one. So let's say let's go over the vertices one by one. So vertex A, the vertices. So A will not be, so we can see that after deleting A from this graph, still the remaining portion of the graph will be connected component. Since like if we remove A and these two edges outgoing from A, still all these like all the components from B to G will still be connected. So not a cut vertex. This will not be a cut vertex as component remains connected. So now we'll look for, maybe I'll just put all of this question on next page, so don't have to go over the figures. Then we'll just look for the vertex B. So for vertex B, we can see that after deleting, like let's see the vertex B, this component A, G, C, D will be a different component from this component of E, F, G. As we can see, because now there will be no edge since B is deleted, all its outgoing edges are deleted. So there will be no edge which connects like this AGCD component and EFH component. So just put these component names in like this notation, this set notation. So AGCD and EFH. B is a cut vertex as its deletion creates components which are AGCD and EFG. So B is a cut vertex. Similarly, we can just go over the other vertices orally, I guess. So C won't be a cut vertex again, since even after removal of C, we can see the whole component remains connected. Now going for D, again, removal of D will still not affect the whole graph as it will still remain connected. So because on removal of D, these two edges will be removed and the remaining portion still is one single component. On deletion of E though, so on deletion of E, we can see that this component FH and this component ABCDG are separated now. Since on deletion of E, these three vertices and these three edges will be cut out. So these two components will be separated out. So for vertex E, maybe I'll not list out this vertex A as, or maybe I'll just. So E is again a cut vertex. Maybe I'll just copy this. A cut vertex has its deletion create two components which are A, B, D, C, G. I'm just going to this ordering A, B, D, C, G, and E is deleted, so FH. So FH is another component. So again, so we see that E is a cut vertex. F will not be a cut vertex since deletion of F still we have only one single component, as you can see. And again for G, on removal of G, these two edges will be cut out. So again, still the remaining component will be one single connected component. So again, on removal of G, G will not again be a cut vertex. And similarly for H, on removal of H on these two edges, still this component FEBCA GCG will remain a single connected component. So yeah, so only B and E are the cut vertices. Remaining vertices are also not cut vertices. So you guys could have like straightforward seen that deletion of B will create two components and like deletion of E will create two components. So these are the only two. But I just like with more practice or like with more time, you guys can identify directly which will be the cut vertex and which will not be. But I guess for beginners, we should try to like try out every vertex and see whether its deletion will create two components or it will not create. So this is a very basic uh, algorithm, or you can say just try to delete the vertex and see whether the remaining component is connected or not. So for beginners, I think this is a better way to see it, the graph. What is the cut vertex and what is not the cut vertex. Otherwise, as we go along the course, or I think in higher algorithms courses, you will see that there are more efficient ways of finding cut vertices and like cut edges. But for now, we'll just be brute forcing and trying out, like trying out deleting all the vertices and then all the edges for finding cut vertices and edges respectively. So let's list out. So cut vertices A or B, comma E. Now coming to cut edges. So for edges, again, I'll just like in a similar fashion, I'll just go over all the edges one by one. So let's look at this edge A comma G, which connects A and G. So on removal of this edge, still the whole remaining component you can easily see is connected. So again, this won't be a cut edge. Similarly, C to G on this deletion also, the remaining component is connected. The remaining this C, D, G, A, E, F, H still is a connected component. So uh, deletion of this GC edge will not again, this GC edge will not again be a cut edge. Similarly, let's go to this CD edge. So on deletion of this CD edge, we'll still be having this as a single component as deletion of CD edge won't create any new components. Similarly for this BD edge, and similarly for this EF edge also, this on deletion of this EF edge, again, we'll still have a single component. Similarly for this FH edge and similarly for this EH edge. So basically what we're doing is we are just trying to delete one edge at a time. So I'm not deleting all of these edges together, just one edge at a time. So deleting just this won't create a new component. Deleting just this won't create a new component. This. Any of these deleted one at a time won't create a new component. Two components basically. So, but deleting on this edge B comma E, as we can see that if we delete this edge B comma E, what happens then is this A, B, C, D, G and this E, F, H components are now separated out. So it's not too difficult to see like since this edge is deleted, so this part and this part will be separated out. They won't have any connectivity. So this B comma E edge will be a cut edge. So this B comma E edge edge as its deletion creates two components A, B, D, C, G and E, F, H. It's easy to see, and remaining edges are not cut edges as we have brute force and tried out every edge. So remaining edges are not cut edges. So for answering this cut edges part, I'm also underlining the correct answer. So only this E comma E. So this B comma E edge is a cut edge and this B comma, and surprisingly like these two vertices were also the cut vertices. But note that this is not a rule of thumb to go by that. Uh, So basically what I'm saying is that it is not always necessary that you can just like suppose there are some cut vertices A, B, C, D. So A comma B will be a cut edge, or suppose if A comma B is a cut edge, then A and B will be cut vertices. So these two here it is just by coincidence that these two things are the same sort of. But here we are only removing a single edge, like B comma E, a single edge is removed. But on removing cut vertices, we are removing actually all the outgoing edges. So these two are different things. Don't be confused that you can just directly say that cut vertices are B and E, so cut edge will be B comma E. So you'll have to try it up. Try it out. It is not necessary that if these two are the cut vertices, then this will be uncut edge. So we have to try it. That's what I'm actually saying. So we have to always try out. Here it was just coincidence that here also we got B and here we also got B comma E. So okay. So I hope it's clear. So let's move on to the next question then. So third question is asking us. So I think today's session will be long and see. So the number of components in a Kn and Cn respectively are. So we guys, you guys must have already seen in lectures what is Kn. So Kn is nothing but the Kn represents a complete graph on n vertices. Since all of the edges are so a complete graph is a graph where all edges are present. So all possible pairs of vertices are connected by an edge. So uh, this is a single connected graph, right? Connected graph, since every pair of vertices already has an edge with each other. So it's already a connected graph. So it means that since it is connected, it will have only one component. Component is something So uh, by definition, basically component is something which is the maximal connected part of, you can say. So here, what I mean to say is the component is something like, let's say if the graph is two components, then it means that there are two connected parts of the graph, both of which cannot be connected by each other. So one component of a graph is a part where every pair of vertices can be connected to each other. So here actually the graph has exactly one component, since every pair of vertices in this graph can be connected with each other. But suppose here in the earlier question, suppose I removed this as B comma E, then actually there were two components in this graph, this A, B, D, C, G and EFH. Since in each of these single components, like in this EFH component, every pair of vertices could be connected to each other. And similarly in A, B, D, G, C also, every pair of vertices could be connected to each other. But any two vertices which belong to different components cannot be connected with each other. So after removing B comma E edge here, we could not connect B with E or B with F or B with H. So that's how you can see what is a component. That's the basic intuitive definition of a component, or yeah. So Kn is a complete graph, so it is a connected graph, so it has one component. Similarly, what is Cn? Cn is okay. Cn is a cycle of n vertices. So you guys already know what is a cycle. So Cn is nothing but a graph which contains only a cycle on n vertices. So here also we can see, like in a cycle, every pair of vertices can be easily connected to each other. Like by going along the cycle, you can go in clockwise direction as well as anti-clockwise direction, doesn't matter. But every pair of vertices can then be connected to each other. Like here we can see, suppose in this graph A, B, D, G, C, A, B, D, C, G, like every pair of vertices can be connected to each other via this cycle. Like A comma C pair of vertices can be connected using this A, B, D, C path or AGC path. So two paths are available using this cycle. One is counterclockwise, one is clockwise. So yeah, that's what I mean. So here also every pair of vertices can be connected to each other. So again, a connected graph. So since it is a graph which is connected with every pair of vertices can be connected to each other, so it's also a single component. Nothing too difficult here. So yeah, so Cn is also a connected graph, and so it also has one component. So number of components in Kn and Cn both should be one. So answer should be option D, which is 1, 1. So D is correct. Okay. Now comes a bit more interesting question. The previous questions were pretty straightforward and just using the definitions which which you guys have already seen in lectures. So now we'll be using the theorem which we discussed in lectures. So the question is asking us which of the following is a graphic sequence. So a graphic sequence, if you guys remember what was a graphic sequence. So a graphic sequence is basically uh, given this sequence of numbers, can we have a graph where this sequence corresponds to degrees of vertices of that graph? So if like let's say this, let's consider this option A sequence, this 5 3 3 2 2 1 sequence. So it will be graphic if we can make a graph of 6 vertices, since there are these 6 numbers here. If we can make a graph of 6 vertices such that one vertex has a degree of 5, 2 vertices have a degree of 3, 2 have a degree of 2, and one vertex has a degree of 1. So this was the definition of graphic sequence, just reminding you guys. So how to find whether a sequence is a graphic sequence or not, that also has been discussed in the lectures. So for that we use Havel-Hakimi theorem. So Havel-Hakimi theorem to find whether a sequence is graphic or not. Right. So Havel-Hakimi theorem, you guys, I expect you guys to already know what was the Havel-Hakimi theorem. So what we say is this will be a graphic sequence if and only if suppose we remove this 5 and decrease for degrees of like the first 5 entries by 1, then that sequence should also be a graphic sequence. If that is not a graphic sequence, then this sequence is not a graphic sequence. So like let's just go option by option to check which of the following sequences are graphic sequences. So we'll go by option. So let's try out the sequence in option A. So one thing to note is that, okay, I'll just come to this. I'll just try to solve this one. So using in Havel-Hakimi theorem, so we can make basically series of sequences, if you guys understand what I mean. So this was the first sequence which we need to find whether it is graphic or not. So using Havel-Hakimi theorem, this can be converted to another sequence and the question of whether that sequence is graphic or not. So how to convert this to another sequence? What we do is, so we see the largest entry of, so first of all, we sort this sequence in non-increasing order. So here we already see that the sequence is not in non-increasing order since the values are decreasing, going on right or staying equal only. And then we take the largest entry, which would be then the leftmost entry of the sequence. And let's see here the value of that entry is 5. So now what we do is we take the next 5 entries of this sequence and decrease all of those values by 1 and delete this 5. So that is how we construct the second sequence using Havel-Hakimi theorem. So again, reiterating the procedure, how we construct another sequence from initial sequence. What we do is we first of all sort the sequence in a non-increasing order. And then what we do, we take the leftmost value of that sequence. We first of all, we delete this number from the sequence. And also we decrease like, let's say the value of this largest entry was 5. We can see here it was 5. So then we decrease the values of next 5 entries by 1. And we repeat this procedure again. So here what I'm saying is what we'll do is first of all we'll be deleting this 5. So after deleting this 5, what part of the sequence remains? Only 3, 3, 2, 2, 1. Right. But another thing what we are going to do is we are going to, since we have removed this 5, we'll be decreasing values of the first 5 entries by 1. So in this part, we'll decrease the values of first 5 entries by 1. So as we can see here, there are 5 entries only. So we'll be decreasing all of these values by 1. So this 3 will become 2. This 2 will be, this 3 also becomes 2. This 2 becomes 1. This 2 becomes 1. And this 1 becomes 0. This is the second sequence which we obtained from the first sequence of using Havel-Hakimi theorem. So we can see like first it was a sequence containing 6 numbers. Then it has reduced to a sequence containing 5 numbers. Again, using Havel-Hakimi theorem, we'll reduce it to a sequence of 4 numbers. So again, how will we do this? So again, we first of all check that it is whether it is in non-increasing order. So here we can see that it is in non-increasing order since no value increase going towards right. So now we pick the leftmost entry, which is this 2, remove this 2. So the remaining part will then be 2, 1, 1, 0. And then what we do, since we had removed this 2, now we need to reduce the first values of first 2 entries by 1. So this 2 will become 1 and this 1 will become 0. Since we had removed 2, so we need to reduce values of only 2 entries by 1. So we have decreased values of these 2 entries by 1. So now we get this sequence, which is 1, 0, 1, 0. But it is uh, not in a non-increasing order, right? So for applying Havel-Hakimi theorem, you should always ensure that the sequence should be non-increasing order. So here, since it is not in non-increasing order, we'll sort this sequence. So 1, 0, 1, 0 instead can be written as like 1, 1, 0, 0, the swapping out the 0 and 1. So now this sequence is in non-increasing order. I hope it's clear to you guys how I arrived at this. So now this sequence will again use the Havel-Hakimi theorem on this. So we'll remove this one and this one will instead be written now as 1, 0, 0. And then what we do, since we had picked this one, so one first entry of this sequence will be reduced by 1. Value of first entry will be reduced by 1. So this one will become 0. So this is the final sequence which we arrive at using the Havel-Hakimi theorem. I hope it's clear to you guys how I arrived at this. So this 0, 0, 0 sequence, as we can see, is clearly a graphic sequence. Since maybe I'll just write it down. But this sequence is this sequence is graphic as it can be realized by 3 isolated vertices. So what I mean to say here is that suppose we have to construct this sequence. So the final question, the initial question of 5, 3, 3, 2, 2, 1 is graphic or not, is reduced to whether this 0, 0, 0 sequence is graphic or not. And this can be easily seen that this is graphic basically, that basically there is a graph where basically there's a graph of 3 vertices and all the degrees of all the 3 vertices is 0. So we can see that this can happen when like there are 3 vertices in the graph and then there is no edge in the graph. So this is what I mean by 3 isolated vertices, that there is no edge in the graph. All vertices are on their own. So degree of all of these vertices will be 0. So this 0, 0, 0 sequence is graphic sequence since it can be realized using this graph. And using Havel-Hakimi theorem, since 0, 0, 0 was graphic, the initial sequence would also be graphic. So option A is a graphic sequence. So A is a graphic sequence. So basically, so the question of constructing a graph for this is just reduced to constructing a graph for this. And we can make a graph for this easily. So option A is a graphic sequence. Now coming to option B, we'll just be checking all the options one by one so that you guys can see when can we rule out that this is not a graphic sequence and when can we say that this is a graph. What is a graphic sequence? So again, we'll go to option B, which is the sequence. Let me just copy the sequence. So the sequence is this 2, 1, 1, 1, 1, 1. So using again Havel-Hakimi theorem, what will happen is we'll first of all take the we'll take this 2 and remove this 2 and write out the remaining ones as it is. And then since we had removed this 2, so we need to decrease the values of first two entries by 1. Since we had removed 2, so we need to reduce values of two entries. So we'll take this one, reduce it to 0. We'll take this one, we'll reduce it to 0. Yeah, so now we are right at the next step. But in this step again, we see for applying Havel-Hakimi theorem, the sequence should be sorted in a non-increasing order. But here we can see that it is not in non-increasing order since like 1 comes after 0 and this 0, 1 is a increasing part of the sequence. So first of all, we'll sort it in non-increasing order. So non-increasing order for this will be like 3 1s coming together, then the 2 zeros coming. So that's not too difficult to see, I hope. So we'll just write it down as these 3 1s coming together and then the 2 zeros. So I've just sorted the sequence to apply. Now we can, since the sequence is again in non-increasing order, we can again apply the Havel-Hakimi theorem. So how can we apply the Havel-Hakimi theorem now? It just says that again we remove just this one and keep the remove the first entry and keep the remaining entries. So we'll keep these entries. And since we had removed this one, since we had removed the value 1, so we'll be reducing only the first number by 1. So this one will reduce to 0. So again, applying Havel-Hakimi theorem. So again, we see that this 0, 1, 0, 0. The 0, 1, 0, 0 is again in a non-sorted, is again not in a non-increasing order since a 1 is coming after 0. So we can't apply Havel-Hakimi theorem directly here. So again, will be like, first of all, we can just directly see also in this step that this 0, 1, 0, 0 is not a graphic sequence since it says that 3 vertices should not have any edge and one vertex should have a single edge going out of it. So this cannot be possible since we are talking about simple graphs and no self loops in the graph. So the edge originating from this vertex should be going to another vertex. So another vertex should have a degree of 1, which is not the case here. So we can directly say also that this can't be a graphic sequence, but just going straightforward more in an algorithmic manner using just Havel-Hakimi theorem. So what we'll do is, so we just arrived this 0, 1, 0, 0 using Havel-Hakimi. We just reduce this to this 1, 0, 0, 0, and then this 0, 1, 0, 0. So we'll again, first of all, sort this sequence. So since this is 0, 1, 0, 0, we'll sort it in non-increasing order. So this will just instead become like this sequence 1, 0, 0, 0. So now in this sequence, again, we'll try to apply Havel-Hakimi theorem. So how will we apply? So for applying Havel-Hakimi theorem, we'll take this one, remove this one. Then we are left with this 0, 0, 0 part. But also, since we had removed this one, we need to decrease value of one entry by 1. So here we'll get a -1. So now we can easily see that any graph cannot have a degree of -1, right? Degree of every vertex is at least 0. So since we have obtained a negative entry here, so we can just say that this sequence. So basically, Havel-Hakimi theorem just says that keep doing these steps till, and in the end, if you just get a sequence of a bunch of zeros, then that sequence will be graphic, as that can be realized by a bunch of isolated vertices. But at any step, if you get a negative entry, then that means that sequence can't be realized since a graph cannot have negative degree vertices. So this sequence is non-graphic as no vertex can have negative degree. Maybe not no vertex, as a vertex can't have. We can just say as a vertex can't have negative degree. So option A is not a graphic sequence. So option B is not a graphic sequence. Hence option B is not a graphic sequence. Coming to option C. This is option C. So always, guys, the main thing which the main part which I want to focus is everyone will be able to apply generally the Howell-Hakimi theorem. The theorem itself is not too difficult, but a lot of people do this mistake of not ensuring that the degrees are in the sequence is in non-increasing order. So when it is in it is not in non-increasing order, you have to sort it yourself first. So this is a very common mistake, and you guys should try to avoid it as much as possible. So so always try that you ensure always ensure that at each step the sequence remains in non-increasing order. Otherwise, Howell-Hakimi theorem can't be applied. So here again, I check that 654-321 is again in non-increasing order. So I take this 6, I remove this, copy the remaining part here. And now what I have to do is this. Okay, so it's easier question. So what I now need to do is I need to reduce the values of first 6 entries by a 1. So I need to reduce the values of first six entries of this sequence by 1. But here I can see that there are only 5 entries, right? But this says that I need to reduce the entries of the values of first 6 entries. But no 6 entries are available. Here only 5 entries are available. So uh, here also this sequence won't be graphic. So maybe we can just say that this step only that I'll need. So this 6 basically says that we need to reduce the values of first 6 entries from this as one, but there are only 5 entries available. So I won't be able to like I need to reduce the value of 6 entries, but I have only 5 entries available. So this sequence is non-graphic. Is non-graphic. Why is it non-graphic? As we need to reduce uh, degrees of as after removing the 6, we need to reduce degrees of 6 vertices by 1, but we are only left with 5 vertices. I need to reduce value of 6 vertices by 1, but we only have 5 vertices. So I can't reduce value of 6 vertices. So hence option C is not a graphic sequence. So just to see what's happening here, why is this not a graphic sequence? You can see directly also that here it says that one vertex should have a degree of 6, and there are only 6 vertices available. So in a simple graph, if there are 6 vertices, then a vertex can have only a maximum degree of 5, since a single vertex can be connected to the other 5 vertices only. So in a graph with n vertices, a vertex can have only n minus 1 degree maximum, because that vertex will have to be that vertex can only be connected to the remaining n minus 1 vertices. So the maximum degree on this graph can be 5, but here it says that there should be a degree of 6. So this can't be possible. So that's why this won't be a graphic sequence. So I hope I'm making sense. So now let's come to option D. So again, in option D, we'll ensure that it is in non-increasing order, which has like in the option itself, it has been given in non-increasing order though in the first step. So now since these entries are in non-increasing order, we'll just straightforward apply the Havel-Hakimi theorem. So take this 5, like it's a standard procedure, remove this 5, copy paste the remaining values. And since we had removed this 5, so we'll need to reduce the values of 5 entries by 1. So we'll reduce the value of these 5 entries by 1. So this 5 becomes 4. This 4, this 2 becomes 1, this 2 becomes 1, this 1 becomes 0, this 1 becomes 0. Again, we'll check that the sequence which we have obtained is the non-increasing order. So here we see that it is in non-increasing order since it is 4, 1, 1, 0, 0. So again, we can apply the Havel-Hakimi theorem. So what it says is that we'll take this 4, remove this 4, take the remaining part, which is this 1, 1, 0, 0. And then what we do, since we have removed 4, so we need to reduce values of 4 entries by 1. So these are the 4 entries, so we'll have to reduce all of these by 1. So this 1 will become 0, this 0, 1 will also become 0, 0 becomes -1, and 0 becomes -1. So again, it's easy to see that this sequence is basically. So we can here easily see that this sequence is non-graphic. Again, the same reason as the option B, as a vertex can't have negative degree. So I'll just copy paste the reasoning and not write it again. Okay, so yeah, we are at option D here. So this sequence is non-graphic as a vertex can't have negative degree since these here we have negative degree vertices, so this won't be a graphic sequence. So hence option D is not a graphic sequence. So the correct answer is option A. Option A was a graphic. The question was asking which of the following is a graphic sequence. So only option A was a graphic. B, C, D, we have shown that not graphic. Only option A is uh, is correct. So now coming to the fifth question. So this I believe is very important. I think the similar sort of question is also given in your in this year's assignment. So I'll just say that you should give attention to how to solve this, and like while solving the problem for assignment also you should ensure that the sequence of degrees is in non-increasing order. That's the main step where many people will falter. Otherwise, basic subtraction can be done by everyone. So I don't think it's too difficult to do this, but just take care of the ordering of the non-increasing order. Yeah. So now let's see the fifth question. Again, fifth question is, as far as I remember, very straightforward. So fifth question says that which of the following is not a path from A to H? So a path, as you guys have already seen in the lectures, is a sequence of distinct vertices such that every pair of vertices is connected by an edge in that sequence. Okay, I'll not type out the definition since it has already been covered. So here we can see, let's go option by option, which so we just need to find out from these options, a bunch of options, which of the following is a path from A to H. So the path should start at A and should end at H. And note in a path, always in a path, the vertices should be distinct, the vertices on which we are going. So we can't go to the same vertex twice. That's a basic definition of a path. So let's see this. The first option says A, B, E, F, G, H. So it says that we go from A to B, then so A to B is an edge, so we can go from A to B, then B to E. So B to E is also an edge. Then E to F, E to F is also edge. Then F to G, but we can't. So it says that we have to go from F to G, but from F to G there is no edge here. Even though there might be other ways like going from F to E to H to G, but in a path, every consecutive pair of vertices should have an edge between them. Not just a path, but exactly an edge. So since there is no edge from F to G, so from F to G, there is no edge. So this is not a valid path. So I'll just type it down. Option A, not a valid path, as no edge between F and G. So I hope I'm making sense. So similarly, let's go to option B now. So how have I made sense? Like, why is it not a valid path? So since there was no edge from F to G, so every pair of vertices, consecutive vertices in a path should have an edge, and F to G was not an edge, so this is not a path. So now going to option B, which is A, B, C, H. So let's go from, so we can go from A to B, since this is an edge, then we can go from B to C, then we can go from C to H. So here all the vertices which visited were distinct, A, B, C, H, and every consecutive pair had an edge between them, and we started at A and ended at H. So this is a path from A to H. So this is a valid path. So now coming to option C. So in option C, so how we are doing this? So option C says we go from A to F, which can be done since there is an edge. Then from F to E, there is also an edge. Then from F, we go to from E to B. Like I'm just following this. So first we are at A, then at F, then at E, then at B. So first I was at A, then I can go to F since there's an edge. Then from F to E, then E to B, then B to C, and then C to H. So here also there was no repeating vertex, like every vertex was distinct in this path, and every consecutive pair was connected by an edge, and we started at A and ended at H. So this is also a valid path. Now going for option D. So what does this? So this question might seem trivial to you guys, like we are trying out so many options, but I guess this is just so you guys can understand the definition of path and like not make any mistakes. So yeah. So in option D, actually I can directly see that this won't be a path. And why is that the case? Even without going on a trail, like checking whether there consists of an edge between every consecutive pair, we can just see first of all that in this sequence of vertices, in this, like if it was a path should contain distinct sequence of vertices, right? But here I can already see that this C is being repeated. C is coming here and it is coming again here. So this can't be a path. So uh, in a path, so just to remember the definitions again, guys, a path should contain distinct. See, a path is a distinct sequence of vertices. A walk can be something where the vertices need not be distinct. Vertices can occur again, but in a path, vertices should be distinct. So option D, I can directly see that since C is coming again in the sequence, so this is not a valid path. Not a valid path as repeating the repeating vertex. Yeah. Let's go to option E now. What does option E say? Option E is AFEDCS. So first of all, I just see that these all are distinct. So at least the distinct part is taken care of. Then just going on this path where there exists an edge between every pair. So exists an edge between A and F, A to F, then F to E, then E to D, then D to C, then C to H. So here again it starts at A and that edge. Every consecutive pair has an edge and all vertices are distinct. So this is a path. So this is a valid path. Going to option F. So in option F, it just says AH, but we can't go from A to H directly since there is no edge between A and H, right? So not a valid path. I hope it's clear. Not a valid path has no edge between A and H. Okay, so I guess we have already got these 6 examples. Maybe you can try out yourself for these in option G and F. So option G and H. Right. Yourself. Maybe I'll just leave it at that. So now let's come to, I guess, the sixth question there. So sixth question says that if an edge is removed from a cycle in the graph, then the graph becomes disconnected. State whether this statement is true or false. So I think this has already been covered in the lectures, or you can just see directly also. So the question is basically asking that suppose we have a cycle on a cycle in a graph, and then I remove one edge from the cycle. So will that graph remain connected or will it be disconnected now? Like, can it be the case that the graph is disconnected if we remove an edge from a cycle? Maybe you guys can, like, this is a pretty simple question. Maybe you guys can try it answering in the. Oh, so Ekta, you are saying that yes. So what are you saying yes to? You are written in chat that yes. So like, can a graph become disconnected after removing an edge from a cycle? Are you saying yes to the fact that it can become disconnected? Or are you saying that it will still remain connected? It will get disconnected. Okay, I think Aditya, this won't be the case. So intuitively, why you can see that this won't be the case? Like suppose I have a cycle of vertices, right? So in a cycle, what this means is that like there is a cycle that these edges, some edges are forming a cycle. So yeah, Khushi has written false, and yeah, so Khushi has written the correct answer. So maybe I'll just explain it basically. Suppose we have a cycle of edges in a graph, and one of those edges gets deleted. Only one of those edges is getting deleted. So then still the graph will be connected as between every pair of like in every between in a cycle between every pair of vertices there are two kinds of path available, as I discussed earlier also, a clockwise path and an anti-clockwise path. So when an edge gets deleted, either the clockwise path gets deleted or the anti-clockwise path gets deleted, but both of them don't get deleted. So graph won't become disconnected. So just to illustrate my point, I'll just come to one of the previous diagrams again. So just forget this EFH part. Just focus on this ABDCG part. Suppose this was the cycle given to us in this graph. And suppose I remove this edge B comma D. So still every pair of vertices will remain connected here. And why is this the fact? Since this B comma D, uh, there are two paths from, like, let's say let's consider the vertices A and C. So there are two kinds of paths between A and C. One path is which goes in the anti-clockwise direction, that is AGC, and one in the clockwise direction, which is ABDC, right? So out of these two paths, suppose I have deleted this BDH, then this path will get destroyed. This ABDC path is no longer present, but this AGC path will still be present. So there are two paths, like clockwise path and anti-clockwise path. And so the edge which gets deleted will either lie on the clockwise path or the anti-clockwise path. It can't lie on both paths, right? Since we are deleting only single edge, so the edge can be either AG or GC. In that case, it will belong to anti-clockwise path, or otherwise it will belong to the clockwise path. So in both of these cases, then, like, suppose here the edge was belong to, like, if VD was deleted, it was belong to clockwise path. So clockwise path gets destroyed, but this anti-clockwise path still remains. So by this sort of reasoning, we can say that every pair of vertices will still be connected. Since every pair of vertices will still be connected, so the graph will still be connected. So in a cycle, deleting any edge won't disconnect the graph. So you could have also, you can also see this in this example only, basically this question. Like this question was asking what are the cut edges and cut vertices in the following graph. So here for cut edges, I told you guys that you can just remove every edge at a time and check whether the remaining component is connected or not. But by going by the logic of the question which I just asked earlier, so any edge which belongs to a cycle, its deletion won't affect the connectivity of the graph. The graph still remains connected. So every graph which is part of a cycle won't be a cut edge. Since deleting that edge won't make the graph disconnected, so it won't be a cut edge. So we can see that all of these edges of this cycle and of this cycle EFH and this cycle ABDCG won't be cut edges. And that can be seen in the answer also, that the cut edge was only B comma E. And this B comma E does not belong to any cycle. So yeah, I hope it's a bit more clear to you guys what I meant to say. So since like all other edges are part of some cycle, so that's why they are not cut edges. This big, so you could have directly argued that all of these edges and all of these edges won't be cut edges, and you'll just have to check for this BE edge using that claim that if an edge is removed from a cycle, then the graph remains disconnected. This is false. So basically the correct statement is if an edge is removed from cycle, then the graph still remains connected. So is it clear to you guys now? Aditya, uh, is my point clear now? Like why is this statement false? Maybe you can type out in chat or just put a thumbs up. Okay, cool. It's clear to you. Nice. So the answer is false. And I'll just type out the correct statement. If an edge is removed from cycle in the graph, then the graph still remains connected. Oh, and also we are assuming that graph was initially connected. So I guess, yeah, that's the point. So in a connected graph, so if the graph was earlier only, like if the graph was earlier only disconnected, then deleting edge after the deletion of an edge, it will still be disconnected. So no point in that. So that's why here it was written as becomes, not is or something like that. So that's just English. Okay, I guess my point is clear to you guys. So let's just move on. Now coming to seventh question. So seventh question is for a simple graph with vertices. So okay, so I think I missed an n here. So a simple graph with n vertices. So there are n vertices in a graph, a simple graph. How many subgraphs can be constructed such that the subgraph is an induced subgraph as well as a spanning subgraph? So just to make you guys remember the definitions. So first of all, what was a subgraph? So subgraph is a graph containing a subset of edges and vertices of the original graph. So a subgraph is nothing but just you take a graph and its subgraph will be you just take any subset of edges and any subset of vertices, then that will become a subgraph. So what is an induced subgraph? So induced subgraph was subgraph where uh, okay, I think I'll have to write this definition out formally, but maybe I'll just skip writing out these definitions. Like I think these definitions have already been told to you guys in the lecture. So I think like writing it again in the formal notation will be a bit redundant and like a waste of time for everyone. So maybe I'll just remove these definitions. So I hope you guys remember the definitions. So let's just start out simply by I'll just only discuss what is a subgraph. So subgraph is nothing but a subset of vertices and a subset of edges of a graph. And what was an induced subgraph? So induced subgraph is nothing but let's say we take a subset of vertices of the graph and all the edges belonging to the original graph between these vertices should also belong to this induced subgraph. So I think you guys might remember. So I hope you guys remember what the definition was. I'm just putting it informally again. So what is basically an induced subgraph? Here you just take a subset of vertices. So like in a subgraph, you take a subset of vertices, but there you in a subgraph you could pick any subset of edges also. But here in an induced subgraph, what we do is we take any subset of vertices and then we take all the edges which have both endpoints as these vertices, two of these vertices from the original graph. So this was the definition of induced subgraph. And what is a spanning subgraph? A spanning subgraph is just a subgraph which contains all the vertices of the original graph. Like in a spanning subgraph, you can skip out on edges, but you need to include all the vertices. And here in induced subgraph, sort of you can think of it as you can skip out on some of the vertices, but whatever vertices you have to have all the edges of between those vertices which belong to the original graph also. So maybe I've just put the definitions informally. You can just visit if you don't remember this definition, you can revisit the lecture again. Like there you can see these formally also, but I believe this is a very straightforward question. So like how many subgraphs can be constructed such that the subgraph is both an induced subgraph as well as a spanning subgraph? So would anyone so anyone will like to answer this question in chat, like how many subgraphs can be made such that the subgraph is induced as well as spanning? Yeah, Khushi is writing only one itself. So yeah, Khushi is correct. So answer is only one. And what subgraph will it be? The subgraph will be the original graph itself. So why is this the case, guys? So basically a subgraph which is induced subgraph as well as a spanning subgraph will be the original graph itself. That's what we are claiming. And why is this the case? This is the case because it can be informally seen is as since it let's say like G prime is a subgraph. What is spelling mistakes here? Let's say G prime is a subgraph which is induced as well as spanning. So maybe I'll just say let's just define some notation for writing out the solution. Uh, let's assume graph G as the original graph. So G contains the vertices E and the edges E, and G prime is a subgraph. So let's say G prime has vertex set as V prime and the edge set as E prime. So let's assume G is V comma E and G prime is V comma E, V prime comma E prime is a subgraph. Let's assume G is the original graph. So G is the original graph and G prime is the subgraph which is induced as well as spanning. So I'm going to prove to you guys that G is equals to G prime. So how am I going to prove that? So let's just take first, since G prime is spanning, G prime is spanning. So by the definition of spanning, the every vertex of every vertex of G should also be in G prime. So we can say that V prime will be equals to V. So this is basically the definition of spanning, that V prime should be equal to V. So, and also what we can see is also as G prime is induced, every edge U every edge, yeah, maybe we can just write U comma V of E, here U and V both lie in V prime. Okay, maybe I'll just write down that maybe I'll just write it this way only. So, so basically, let's take any edge U comma V of E, and such that U and V both lie in V prime. So for any subgraph, basically G prime is a subgraph. Here we have taken a big subset of vertices as well as some subset of edges. So what I mean to say here is that every edge of E which I pick, where U and V both lie in V prime, like so I'm just writing out the basic definition of induced subgraph only. So every edge which I pick of E, where U and V both lie in V prime, then this edge should also be belonging to then U comma V should also belong to uh, E prime. This is sort of a bit of a formal definition for an induced subgraph, that every edge where both endpoints lie, original edge whose both endpoints lie in V prime, that edge should lie in E prime. So this is the definition of a induced subgraph. So we get a better definition we get a more formal definition for induced subgraph. So by this definition, uh, since G prime was spanning, we have already proved that V prime equals to V. Since V prime equals to V, so in this statement, since this statement, every edge U comma V where both line V prime should also belong to E prime. So this statement just reduces to the fact that maybe I'll just copy paste this statement. Every edge U comma V. Since here it was V prime equals to V, so I'll just substitute instead of V prime, V only. So every edge U comma V of E, where U and V both lie in V, then U comma V should also belong to E prime. So, Khushi, you have written in chat that G prime is induced. It means V is equals to V prime. No, Khushi. Since G prime is spanning means V equals to V prime. The definition of a spanning subgraph is that V equals to V prime. But the definition of an induced subgraph is something like this, that suppose we take two endpoints U comma V of V prime. Then if U comma V is an edge in E, then it should also be an edge in E prime. So basically every pair of edge of the original graph should also be present in the subgraph, provided we have picked those vertices in the subgraph. So I think I'm making it a bit more confusing by saying these definitions differently every time, but you guys, I'll just say that you guys should just go to the lectures to get a proper definition, and you guys can stick to that. There are multiple variations, but saying all of those variations out loud will just confuse everyone. So yeah, so I'll just say this. So since V prime equals to V, every edge U comma V of E where U and V both lie in V, was basically what this statement is saying is that for every edge U comma V of E where U and V both lie in V, so this will basically mean that every edge of V. So since so for a graph G, every pair of vertices will lie in the vertex set itself, right? So this means that for every pair of vertices, we take every edge which is present in the vertices. So this basically means that we take all the edges of the original graph and they should also belong to the set E prime. So what I just mean to say is that this just means that every edge of you guys can check this claim yourself later also, like you can try to see it yourself. It's very intuitive. I'll just type this up so it's a bit more clear to you. So this just means that every edge of E should also be present in E prime. So E equals E prime. So we'll basically get this sort of scenario. So here, so we first took the definition of spanning subgraph. From that, we got V prime equals to V. Then we took the definition of induced subgraph. And induced subgraph, we said that uh, every pair of vertices between the subgraph every pair of vertices in the subgraph should have an edge if they have an edge in the original graph. So from that part, we got that every edge should be present in uh, every edge should be present in the subgraph also. So maybe you guys can see these claims later after this session gets over also. And if it's still not clear to you guys, then you can ask this on discussion forum also. Here, basically what we have proved is that V prime equals to V and E prime equals to E. So I just say that since V prime equals V and E prime equals E, so prime equals G. So G prime can only be equals to the original graph G itself, since vertex set and edge set both are now equal to each other. So yeah, that's it guys for this solution. You guys can try to see this later also, since this PDF will be put up, and try to understand the solution again. But you can see this intuitively also, like I'm able to see this intuitively. Maybe you guys can also try to see this intuitively. So yeah. So okay, so I just saw a question in chat. So Tehseen was asking for something for the related to previous question. So sir, if cycle will break, then it will not make cycle. Yeah, Tehseen. Yeah, so Tehseen is saying for the sixth question that if an edge is removed from a cycle in a graph, then the graph becomes disconnected. Should it true or false? So for this question, Tehseen is saying that thus since an edge is removed from cycle, it won't remain a cycle. Yeah, Tehseen, you are correct that it won't remain a cycle now, but still it would still be connected, right? We just have to answer whether the graph will become disconnected or it will still remain connected. So after the removal of the edge, the graph will, yeah, it may be the case that the graph now does not contain any cycle. It can definitely be the case. But all we want to say in this question is that still it won't be disconnected. It will still form a connected graph. It can be a graph which is connected, but cycle-less, like basically a tree. A tree is something which is connected, but not a cycle. Tehseen, I had told you guys earlier also, right? That it won't, you are saying that it will be a disconnected graph. I just argued a while ago that it won't be disconnected since an edge is removed. So there can be two sort of paths between vertices, like the clockwise path and anti-clockwise path. After removal of an edge, only one path can be destroyed. So other path still remains. So the graph will remain connected. It won't get disconnected. It will still be a connected graph, although it may not have any cycles now. So is it clear to you, Tehseen, what I mean to say? Like the graph will still be connected. It's just that it may or may not have cycles anymore. But connectivity and having cycles are two different things. So yeah, okay, it's clear to you. Nice. So okay, guys. So maybe we'll just come to eighth question now. Again, eighth question is again asking something related to a bunch of definitions of the graph, like what is a trail, what is a cycle, what is a circuit. So yeah, maybe we'll just go over this, or maybe I'm thinking that uh, maybe we can just try it out. We are doing these sort of questions. We have done this sort of question earlier also. We'll just do this a bit more faster. So we'll just see which of the following options are correct for this graph. So we'll see that. So the first question is asking whether this sequence is a cycle or not. So just going over the sequence is D to E, then E to F, then F to G, then G to C, and then C to D. So this is a cycle, right, guys? So this is basically referring to this cycle, D, E, F, C, G, C, D. So a cycle is something which has only the first and last vertex as the same, and all other vertices are distinct. So here that part is satisfied, and every consecutive pair is connected by an edge. So option A is a cycle. If you guys don't remember all these definitions, like what is a cycle, what is a trail, or what is a circuit, I will recommend you guys to like sort of look into them and at least uh, like remember the basics. Like you should always know what is a cycle as well as a path. For all these different other definitions, like what is a trail, what is a circuit, you can always try to look it up online, but it would be preferable if you guys maybe like remember these definitions. So it's so that it's mostly so that it's immediate to you guys when something of this sort of is asked, that what is a trail or what is a circuit. So to answer that faster, it will be better if you guys can remember the definition. So myself, I also only just generally remember the definition of cycle and a path, and other things I just generally Google up. So yeah. So let's go to option B now. So option B is basically whether this sort of sequence is a trail or not. So trail is something which is uh, so as we can see, a trail is a walk in which all edges are distinct. So trail is something where all edges are distinct. So here, since what is a trail? So a trail is basically a walk in which all edges are distinct. So here we'll start with like from H and like let's go over the sequence, and we just need to find that we just need to ensure that all the edges which we are working on are distinct. So we are going from H to B, just covering this option. So H to B, then B to D, then D to C, then C to G, then G to F, then F to D, then D to A. So I guess every pair of like every edge which we have covered is distinct. Like we have not covered the same edge twice. So we first came here, then we went here, then we went here, here, and then we came up. So I think this is a trail since we have been going in. So I believe it is a trail since we have not repeated any edge. I'll not cover all these options. I believe this is a bit of a boring question. This is getting boring since we have discussed these sort of questions earlier also. So I'll just leave these options to you guys as an option. Option C, D, E. Try it yourself. So yeah, it's nothing too fancy. So Tehseen, sir, what is making cycle formate? Tehseen, what question are you talking about in option B? So option B, this is H, B, D, C, G, F, D, A. Oh, so I guess you are saying that this is forming a cycle, like this DCGF is a cycle. So I don't think this is an issue. Like in the definition of a trail, you don't need it to be like it can also contain a cycle. I think the only requirement for being a trail is that every edge should be distinct. Every edge should not be like every edge should be covered only once only. Like so, any no edge should be covered twice. So this is the only definition for a trail. So in option B, since every edge is being covered only once here, so like if it doesn't matter whether it's forming a cycle or not in definition of a trail. So yeah, maybe I'll just give the answer to you guys for this. So you guys can like later verify whether your solution was correct. I already have the answer written now, so yeah, I'll just give the answer option A, B, and E are correct. And try this later. I won't be getting into this now. Earlier also I gave something like try it yourself. So here also I'll just give the correct options to you guys. So you guys can just see whether your solution was correct. So options. So this is question number 5, I believe. Yeah. So for this, A, D, and F were correct. Options A, F. I don't need to do it right now. I'm just typing out the answers in front of you. Like when this document is uploaded, you guys can try out these problems and verify your answers. So yeah. So yeah, I think that it is forming a cycle from F to D. That's you're correct for this option. Like this trail is forming a cycle, but I don't think that's a problem. Like a trail can form a cycle. The only requirement for being a trail is that every edge should should be walked at least once. Like no edge should be walked twice. So here we are going to D 2 times, but we are going to vertex D 2 times. Like no edge is being repeated in this. Only the vertex is repeated. For something to be not called a trail, we need an edge to be repeated. So I hope the distinction is clear to you. Sir, for maybe you sir for trade track. I'm not able to understand your point. I think like just try to understand. Like what I'm trying to say is that a trail can contain a cycle. Like no like there is no issue with forming a cycle. The only thing that a trail should not do is repeat an edge again. So there is no edge being repeated. Vertices can be repeated. That's just my point. So maybe if you are still a bit unclear with these definitions, you can ask this in discussion forum, I guess, to get better answers for this or like properly typed out answers. For trail straight track, maybe you can take this up like after this session and on the discussion forum. Like, let's just leave this. I don't think it's that much important. Also, like knowing the exact definition of trail and something. Like, these are some things which you can always Google up. So maybe I'll just leave this question at this. Let's just go to the question. So let's come to this ninth question then. So in this ninth question, which of the following statements is are true? So we are given 3 statements and we need to tell which of these statements are true or false. So first, I believe these properties have been discussed in the lectures already. So it is something which has these options are something which are directly quoting the lectures. So first option, if there is a walk from P to Q, then there must be a path from P to Q. So I believe this has been covered in the lecture and this has been proved also that this first statement is true. Like if there is a walk from P to Q, so a walk can what was the difference between walk and a path? A walk can contain cycles, a path cannot contain a cycle. So basically, if there is a walk from between 2 vertices, then there also is a path. So this is statement 1 is true. And similarly, like I'm just doing this orally since this is a straightforward application of what has been discussed in the lectures. So, and second question is the number of edges in a tree is equal to 1 less than the number of vertices. So this has also been shown in the lecture that number of edges in a tree, so if the number of vertices are n, then the number of edges will be n minus 1. So this is what the statement is saying. And similarly, the third question, the third option, like, is saying every graph has an odd number of odd degree vertices. So I guess this is something which was called the handshaking lemma, right? Every graph has an odd number of odd degree vertices. So maybe I think I can discuss this all because already. Uh, 1 second, guys. So sum of degrees is E1. So no, E1 degrees vertices will be. So I guess you guys must have already seen this in. Yeah, this was handshaking lemma, right? Like every graph has an odd number of odd degree vertices. This is not true. Like the handshaking lemma says that every graph that has an even number of odd degree vertices, right? So this statement 3 is incorrect. Yeah, Khushi is writing correctly in the chat that the answer is true, true, false. So the handshaking lemma basically says that every graph has an even number of odd degree vertices, and that has been proven already in the lecture. The proof is also not too hard. So this option is saying that is an odd number. So this statement is incorrect, and the first two statements were correct. So which of the statements are true? So only statement 1 and 2 are correct. So yeah, I hope it's clear. Like these were just straightforward uh, direct statements which were related to the lecture. So yeah, I'm not putting too much emphasis on this. So now comes the interesting question, the last question. So yeah, Khushi and George, you both have written true, true, false. So your answers were correct. So now let's move on to the last question for the day. So this is a bit more interesting question and you will need a bit more time to answer this. So suppose every vertex in a simple graph has a degree of at least k. So basically it's saying that we have a simple graph and every vertex of the graph has a degree of at least k. So prove that the graph has a path of length at least k. So this question is just asking. So we already remember the definition of a path, that a path is a sequence of vertices which are connected by edges and all the vertices should be distinct. So now what this question is asking us is that so a graph can have a large number of paths, right? An exponential number of paths. So what this question is asking us is that graph will have there will exist a path in this graph. Like if degree of all of the vertices of that graph is at least k, then that graph will have a path which is of length at least k. And what is length of a path, guys? So length of a path is just the number of vertices in that path, number of edges in that path. I think it's already known, but I'll just write it down. Also, length of a path is equals to number of edges in a path. So does anyone have any ideas on how to proceed with this problem? Maybe you can type it out in chat. I think it's like more interesting than the previous problems which we have discussed, since this involves a bit more thinking on your side rather than direct applications. So first of all, the question I believe is clear to everyone that suppose we are given a graph in which every vertex has degree of at least k. Then we need to prove that there will exist a path, like not between every pair of vertices, but there will exist at least one path between some pair of vertices, let's say, such that the length of the path is at least k. So we don't need to show that length of every path will be k, because like obviously there will be like one length paths also, like an edge is also a path. So, but we need to show that there will exist at least one path which has length k. So this is a bit more interesting question. So maybe I'll just start solving this question because I believe it's not too easy to see. So we'll try to prove this by, let's say, contradiction. Aditya, okay, in a path, every node's degree is 1. Okay, but that doesn't mean, Aditya, that doesn't mean that the degree of that node in the actual graph is 1, right? A graph can, the vertex in the graph can have a degree, a very large degree also, but the edge contributing to the path is, let's say, only one edge. But like in a path, even if the node's degree in the path is 1, it does not mean its degree in the whole graph is 1, right? In whole graph, it can have, let's say, like 5, 10 more edges, like 100 more, like any number of edges, right? So this sort of argument is not something which we'll get to you. So basically, like, so what I'm trying to say is that even if like, a path will have, okay, you're saying that every node degree in a path will be 1 or something like that, but like the node's actual degree in the graph will be more than that, right? A path is selecting some edges out of all the edges. So this doesn't mean that uh, every node degree in the whole graph will be 1. It can be more. Like, let's just see in this question only. So let's say this DBC was a path, right? In this graph. So here you like, but D has a degree of 4 here, degree of 5 here, even though DBC is a path. So in a path, every node degree is not 1. Like it can be arbitrarily large. So it's not that simple. Try to like, I always feel that like making wrong claims is a more serious sign of you not understanding the solution, because it shows that like you have missed some concept, or you have misrepresented some concept, or misunderstood some concept basically. So if you always try to think first that whether your claims are correct and why are they correct, rather than making incorrect claims. So yeah. So maybe I'll just proceed with this. So we'll try to prove this by contradiction. So we have already seen like how does a proof by contradiction go. So basically we have to prove that the graph has a path of length at least k. So for using contradiction, we'll assume that the graph does not contain so we'll assume that does not contain any path of length greater than equals to k. What this means is that so all paths in G are of length less than equals to k minus 1. Right? I hope this claim is clear to you guys. So suppose this statement was incorrect, that the graph has. So G is a graph. Okay, I'll just. Okay. A graph where degree of each vertex is greater than equals to k, right? So G is a graph where degree of each vertex is greater than equals to k. So now, so the claim says that then this G should have a path of length at least k, right? So in contradiction, we'll assume the negation of this. So for contradiction, we'll assume that G does not contain any path of length greater than equals to k. So all paths in G then are of length less than equals to k minus 1. Right, guys? I hope till this claim is at least clear to you. Like this is just a straightforward claim of the contradiction. I have not yet proved anything. I've just written down how will I proceed. So is this step clear to you guys? Like what I'm writing here. So for writing, okay, Rohit. So it's clear to you. Nice. So yeah. So for proving the contradiction, we have assumed that G is a graph where degree of each vertex is greater than or equals to k. Then we have assumed that G does not contain any path. So all paths in G are of length less than or equals to k minus 1. So now comes the interesting part. So let me just show to you guys this in a form of a diagram. So let's take any path. And then let's take the largest path of G. So basically there will be a lot of paths in G, right? So let's consider the largest, or let's say the longest path. What I mean by the longest path, the path which has the highest length, right? Longest path of G. So then this path will have a length less than or equals to k minus 1, right? Since we have assumed that all paths are of length k minus 1, less than or equals to k minus 1. So this path will also have then less than or equals to k minus 1. Since all paths are of length less than or equals to k minus 1, then so the longest path will also have length less than or equals to k minus 1. Like, this is a very straightforward argument. So now let's just try to see what this path will look like actually. So I've pasted a diagram here. So let's just say this was the path in that graph. Like let's for now assume it was actually of length. Okay. I think I have written one less edge, but I don't think that will matter. So, okay, let's just see. So let's just take this path. Let's say the path goes from like V1 to VK minus 1. And let's just say this was the longest path, right? There, let's consider the longest path of G. This path will have length less than or equals to k minus 1. So let's just take one case, like it could be k minus 1, k minus 2, or anything. So here I see, let's say the length was k minus 2 of that path. So the vertices, the path will have some vertices. Let's label the vertices as like V1, V2, V3, V4 up to Vk minus 2 and Vk minus 1. So since this is a path, all the vertices are distinct. And so like these will be k minus 2 edges between them. So like so from V1 to V2 there will be one edge, then V2 to V3, then V3 to V4. So till Vk minus 1 to Vk minus 2 to Vk minus 1, we'll have a total of k minus 2 edges. So length of this path will be k minus 2. Right, guys? So I have not yet proved anything. I just shown you like what kind of path will this look like. Like let's just take the longest path, then the path will look something like this. So it can also be like this can be Vk minus 1 and this can be Vk, since the path can have a length of k minus 1 also. Like let's just assume this for now. So now what we can see is that degree of V1. So degree of V1. So we also have that degree of each vertex is greater than equals to k, right? So degree of V1 is also greater than equals to k, right, guys? G as degree of all Oh, am I audible now, Khushi? I don't know. I pressed, I think. Okay, am I audible now, guys? I think I just got muted by mistake. Okay, I'm audible now. Nice. So, so what I mean to say is in degree of V1 was greater than equals to K. So V1 should have at least K neighbors. And out of these, they like suppose V2 was a neighbor, V3 was a neighbor, V4 was a neighbor, and all of these Vk minus 2 and Vk minus 1, all of these were neighbors of V1. Okay, guys. Then in that case also, these only constitute like K minus 2 vertices. Like Vk minus 1, Vk minus 2 up to V2. These are only K minus 2 vertices. So V1 will have two more neighbors, right? V1 will have two more neighbors out in like which are not one of these. Which is not one of V2, V3, V4 up to Vk minus 1. Like by pigeonhole principle, we can say. So since V2 Vk minus 1 are only K minus 2 vertices, hence one will have at least two vertices which are uh, not which are neighbors of V1. So which are neighbors of V1 but are not part of this path. I hope I'm clear to you. I hope I'm making sense to you guys. So V1 will have at least K neighbors, and since these edges and these vertices only form like let's say K, these are only K minus 2 vertices. So V1 will have at least two neighbors here which are not part of this path, right? So then what this means is that uh, okay. So what this means is that there will exist. So there will exist a vertex V which is a neighbor of V1 but not a part of the path, right? So it will be a neighbor but not a part of this path. And this is the longest path. Remember, we have chosen this path, which was the longest path. So now what this condition will look like, I'll just show you the image for this. So this will look something like this, right? So there will be this condition will look something like this. So there will be this path V1, V2, V3, V4 up to Vk minus 1. And then there will be this vertex V line like outside of this path, which will have an edge with V1. I hope this is clear to you guys. So and this condition will look something like this. So now what we can say is that now comes the interesting part. So now what we can say is that uh, now let's take this path instead. Like earlier, what we said was this V1, V2, V3, V4 up to Vk minus 1 was the longest path in the graph. Right. Now, what I'm claiming is that there is also a vertex V, which is not a part of this path, but is a neighbor with V1. So now what I can do, I can instead also have a path which starts from V, right? There can be a path V, V1, V2, V3, V4 up to Vk minus 1. So length of this path will be K minus 1 instead. Like if the length of this path was K minus 2, then length of this path which starts from V will be K minus 1. As this path will now contain an additional edge which goes from V to V1 and remaining edges will remain the same. Right, guys? I hope I'm making sense. So now I get, so basically the overview is that after adding this edge, I still get a path, and the length of this path is one more than this original path which I took, this v1 to vk minus 1. But this original path which I took, I assumed it to be the longest path. But I have obtained a longer path in this graph now from v to vk minus 1. So this is a contradiction. If you guys can see. So I took the longest path, which was like from v1 to vk minus 1. But now I'm saying that there is a longer path which goes from v to vk minus 1. So this can't be possible, right? Because like nothing can be longer than the longest path. So we will obtain a contradiction. So I'll just type it down. So we now consider the path v1 k minus 1. This path will have length equals to k minus 1. Okay, so here earlier length of v1 to vk minus 1 was, let's assume length equals to k minus 2. Earlier the length of the longest path was like k minus 2. We assume length of this path to be k minus 2. Like we saw this, but now we have obtained a path which is of length k minus 1. So this path will have length equals to k minus 1. We have obtained a new path which goes from like v to vk minus 1, and length of this is k minus 1. But this can't be the case, guys. But this is a contradiction, as one, maybe I'll just copy paste, as v1 to vk minus 1 was the longest path. So no path can be longer than that. So basically, I have obtained a path from V. I have obtained a path which is v1 up to vk minus 1, which has length k minus 1. Uh, but so the length of this path is greater than the longest path, which is not possible. So no path could have been longer than that, but I actually obtained a path which is longer. So this is a contradiction. Hence, v1 to vk minus 1 was not the longest path. So we arrive at a contradiction. So since this is a contradiction, what we can actually say is that uh, there will exist a path in G which is of length at least, k. Like all paths in G are of length k minus 1 less than equal to k minus 1 is a contradiction. Hence, there will exist a path in G of length at least. So we are done with this. Is this clear to you guys? I think I rushed a bit through it, or like I use some claims like which may not be like directly obvious or not be directly intuitive, but these are pretty straightforward claims. So if you have any doubt, you can ask in chat about this, guys. We have 5 minutes. So the basic outline of the proof was that we just took the longest path in the graph. We assume that, like by contradiction, we assume that all the paths are of length less than or equal to k minus 1. Then out of these paths, we took the longest path. So it should be of length less than or equal to k minus 1. Suppose we took it of length k minus 2. Then we showed that actually there can exist another path which is of length longer than the longest path, which can't be possible. So if you guys have any doubt, we have 5 minutes, we can discuss it. Someone is typing in chat. Also, one thing to note here is that like we had shown that this path will we just showed that this path will have length less than equals to k minus 1. So I assume that length was equals to k minus 2. So you guys might think that this is incorrect, that length can also be k minus 1. Why did I take k minus 2? So same proof also works if we take length equals, it's I would say homework to you guys maybe, like length can be less than equal to k minus 1, right? All paths will have length less than equals to k minus 1. So length can be k minus 1 or k minus 2 or anything. I took k minus 2 and proof for this. So if I take k minus 1, same proof will work, but I'll leave that as a homework exercise for you guys. So same proof also works if we take length equals to k minus 1. Try it yourself. The same proof will work, like this sort of thing. Only like here we had two vertices which are neighbors of V1 but not part of the path. They will have one vertex. So maybe I'll just not say this, but I'll just say try it yourself. So by trying it yourself, like why I'm saying you should try it, because it will first of all give you a better understanding of this solution, and also give you better insights on, like give you some practice on how to prove some sort of stuff. So yeah, I'll encourage you guys to prove this if we take length equals to k minus 1. So same proof will work. You just have to verify the claims. Like why will those claims hold when we take k minus 1 also? So the main argument, I hope is clear to you guys. We just took a path of length k minus 1. Like we just took the longest possible path, and we showed that if the longest possible path has length less than equal to k minus 1, then there will exist a longer path than the longest path, which certainly can't be possible. Like if you take some number which is long, something which is largest, then nothing can be larger than that. So yeah. Okay. So now, Rohit. So yeah, Khushi, you are asking in chat V1 to Vk minus 1 number of vertices k minus 1, right? Yeah, Khushi, number of vertices in the V1 to Vk minus 1 is k minus 1, but length of a path is defined as the number of edges. So let's say, so number of edges will actually be k minus 2. Like let's say there is a path like which goes from V1 to V2. So number of vertices in that path is 2, but number of edges will only be 1, right? The edge connecting V1 and V2. So similarly, till V1 from V1 to Vk minus 1, there will be like k minus 1 vertices, but there will be only k minus 2 edges. One edge from V1 to V2, then V2 to V3, V3 to V4, V4 to V5, and something like that. Yeah. Okay, nice. So Rohit, you are saying you're asking for another proof. Uh, so when k equals to 1, every vertex has degree at least 1, which means graph is connected. Therefore, there exists. So Rohit is trying to prove this by induction in the chart. Assume that has a path inductive set. So maybe Rohit, since we are running out of time, maybe I'll try to answer this later in the chat. Like your Rohit has written an alternate proof in the chat, like which is a bit long. So maybe we can discuss this, like you can discuss this in the discussion forum, or I'll just comment on this proof after the meeting ends in the chat only. So for now, I think like since we are running out of time, we have been routed only like 6 to 8 p.m. slot. So I guess I leave you guys at this, at least this discussion at this, and the remaining questions I can take up like after the meeting ends. So yeah. Okay, so that's it for today, guys. So I hope you all enjoyed the session. So I believe you have a submission for assignment tomorrow or today. I don't remember. So all the best for that submission, and we'll meet again next week. So goodbye for now, guys. I'll just stop the